Welcome to the demonstration corner. Today we're going to talk about measurement of powders by the transient plane source method that is available on our MP1 and MP-V. Classic here, we're going to talk about the methods that are available in our demonstration corner and a little bit of information on each one, and we'll get into the demonstration. So, to my left, your right, we have the guarded heat flow meter. This is following ASTM E1530 for measurement of thermal resistance from thermal resistance and calculated thermal conductivity from -20 to 310 Celsius. Its real unique capability and where it shines is on the measurement of heterogeneous materials. Again, homogeneity, heterogeneity defined in terms of heat transfer properties as how uniform the diffusion of heat is inside your material. So if you think about that, if you have a composite or different layers, etc., if the heat of diffusion is not at the same rate throughout the body of that entire sample, you have a complex sample that's not heterogeneous. It's not necessarily what you see under a microscope. So what we, in some of those situations, depending on a degree of that heterogeneity, with that definition, you might need to measure thermal resistance to get a true value. And that tends to be true for complex composites that are heterogeneous in nature and or layered that are not repeating through the thickness. So this is ASTM E1530 for a thermal conductivity range of 0.1 to 100 watts per meter Kelvin. So that's a very critical instrument in measuring such complex materials, which exists in a lot of engineering projects today. This is another thermal resistance method with calculated thermal conductivity being one of the outputs of the measurements. This follows ASTM C518 and related international standards for the measurement of insulation and construction material. So we have a couple models of this. HFO 100 stands for the maximum thickness of the sample, 100 millimeters or 4 inches. The inside space is 12 by 12 or 300 millimeters squared. And this has, the HFO 100 has a temperature range of, plate temperature range of -20 to 75 Celsius. There is a high temperature version of this that is -30 to 110 Celsius, and that's called HFM HT, high temperature. The accessories you can add to this are specific heat measurement and a high TC kit for measuring up to 2.5 watts per meter Kelvin. There's one other model, and it's called the HFM 50, and that would be everything identical in terms of specifications except for the inside space, it being up to 50 millimeters thick or 2 inches thick and sample size of 8-inch square or 200 millimeter square. And that's designed for insulation and construction materials. So those are our two thermal resistance methods, uniquely important given the industries they serve. We'll be mentioning the MP1. Most of the measurements and demonstration will be shown is on the MP-V, but the MP1 is our advanced measurement platform combining multiple methods of measuring thermal conductivity, thermal diffusivity, specific heat, and thermal effusivity across multiple methods. Transient plane source following ISO 22007-2 for solids, pastes, and powders. For liquids and phase change materials, transient hot wire following ASTM 7896. And there's lots of demonstration videos on our channel that you can check out and see. Of course, this instrument has many capabilities beyond the mid-range MP-V. We invite you to learn more about it, those being temperature, thermal conductivity range, ability to measure a complex material, very expandable rather, and we describe this as future-proofing your thermal-physical characterization needs. The MP-V, which is our mid-range versatile instrument combining a couple methods. We'll talk more about that in a second. We have our focused DHW-L1, which is for liquids and phase change materials exclusively, has our built-in proprietary temperature platform. This has a temperature range, this model of 10 to 200 C. That can be expanded depending on the option that you add to it, cryogenic up to 300 C. And back pressure capability, 20 bar or 35 bar. Why is that important? It allows us to test past boiling points. So again, thermal conductivity, thermal diffusivity and volumetric specific heat of liquids. And phase change materials. Why phase change materials is because there's a special cell that you can acquire with your instrument to account for change in volume so that your sample stays in contact with the testing wire. So it's a really good instrument, really focused on liquids and phase change materials. We have our baby brother to the heat flow meter line, which is our HFM 100, or HFM 25, sorry. It allows you to test up to a thickness of 25 millimeters. It's specifically designed for small format installation, where typically, when you're doing R&D on installation, you want to, from a cost point of view or capability point of view, you're making small samples. You want to characterize those with the proper method. So we designed a heat flow meter to allow you to test samples as small as 2-inch square and thickness range of a few millimeter up to 25 millimeters thick. Next to that is our TPS-3, which is our portable series of TPS for multi-property following transient plane source method, thermal conductivity, thermal diffusivity, and specific heat. One size sensor, easy to use. You can acquire it with a Keithley meter, or if you have your own Keithley meter, you only need the package for the sensor adapter and software. Typically, to the left of that would be our MP2, our measurement platform for portable. So we have 3 MPs, MP1 for advanced, MP-V for mid-range, and our MP2 for portable. That is on its way back from a trade show, and we don't have it, but that is an intelligent portable platform combining almost the same methods that you see in our MP-V and MP1, just very small ranges for specific applications, but quite good performance and versatility. So maybe what we can do is pull a little closer, square on with the MP-V, and we'll talk a little bit about it, and then we'll get into a demonstration of measurement of today. We'll be doing a titanium powder. There you go, titanium alloy. This is typically used in 3D printing. Where are you? There you go. Typically used in 3D printing. I don't know the exact particle size of this titanium powder, but it's sub 1,000 micron, spherical in shape. Why pointing out that spherical in shape is that you'll see when you're testing it in various setup situations, even with change in force or density or pressure, the number's pretty stable. That means the ambient density is very similar to different changes in force to try to affect the density. Materials that have different particle sizes, different particle shapes, and of different densities are much more acceptable. Well, that's why this makes a good demonstration, because we get to show you in different setups and have similar numbers, which you'll see. So again, this is a 3D printed titanium alloy, and we'll be demonstrating that. But a little bit about the MP-V. This was an evolution of our early TPS-2, which was only transient plane source, and we've combined multiple methods into a mid-range instrument. This was really needed by our customers that have that mid-range purpose, that don't need the full capability of the MP1 and need more capability than our MP2, but want the advantage that comes along with multiple absolute methods of measuring thermophysical properties. So the MP-V follows the basic system. You can see the specifications on the website. The basic system, transient plane source, includes the slab module for conductive sheets, as well as the ability to measure bulk, thermal conductivity, thermal diffusivity, and specific heats of solids, pastes, and powders. We combined with the basic system the transient hot wire sensor for room temperature testing for those same thermophysical properties for liquids. So we have 2 methods as a base system to give you full capability of measuring absolute high accuracy for solids, pastes, and powders, and liquids, all within the same box. And and it follows both standards. And there's typically a sample holder here, much like this one, that's part of the base package, and a transient hot wire sensor. All that stuff's coming back from a trade show. This is an optional MTPS sensor. Now, why we call this an MTPS sensor is that it is a permanently assembled single-sided or asymmetric transient plane source sensor, following the same theory as ISO 22, or what same theory described in ISO 22007-2 for thermal conductivity, thermal diffusivity, and specific heat. What is unique about this one, it's permanently assembled and validated and really designed to be convenient, but all the capability of the Symmetric or ISO. Now this one has an additional standard that it follows for thermal effusivity, ISO 22007-7, and that's for measuring one-dimensional and three-dimensional thermal effusivity. We'll be doing more discussions on that. So this is the only asymmetric or single-sided sensor or absolute MTPS sensor, modified version, that follows that standard. So what we'll be demonstrating is when you acquire an MTPS sensor, there's an optional powder cell that you can add to it. All it is a 3D printed part that you clip in, and it leaves a volume. I think the volume is approximately calculatable. It's variable, so I'll just describe the dimensions. That opening that is right over the double spiral sensor below it is 25 millimeters or an inch in diameter, and the height of that is at least 25 millimeters or an inch in height. You don't need to fill the whole height, and that's where that variable part. So how much volume is based off how much sample or powder or paste you put in there. So the variable component could be 5 millimeters to 25 millimeters as an example. So the more powder you put in there, that's sort of what defines the volume. So we'll be just setting this up for powders and setting a measurement, showing the software, as well as we'll be demonstrating a sample setup on Symmetric for an MP1 measurement. We won't necessarily be showing the software to make a measurement, but the Symmetric setup, or two-sided Symmetric using the powder cell. That's if you don't have an MTPS sensor, how do you test powders? It's this way. It's identical for both MP-V and MP1. So we're going to change camera angle here and show the powder setup and move to the software. So ideally, you place your MTPS sensor on a flat surface where you're not getting any vibrations. We're not going to measure a solid, we're going to measure a powder. So hopefully, is that a good angle? Kinda. We're going to pour the powder directly into it and use the weight. We're just looking for the weight. Okay, we'll be using this one. Okay, so I'm going to pour the powder directly onto the sensor. Again, I'll roughly half. And when you're on a material like this that's spherical, similar particle size, if I were to tap that or vibrate it, you're not changing the result a lot because its density is relatively stable, even with those considerations. So, but if you do have a material that's low density, different particle sizes, or different particle shapes, you do have to take care that whatever you do in your setup, that any future measurements you do identical. So if you're doing 3 taps or whatever that might be, you want to make sure that you're repeating that process. So we're going to add a small weight, although when it comes to, again, this density, this stable, this powder that is stable density, it wouldn't make much difference. So symmetrically, I'm going to point at this guy, and we'll show you the setup. So this is the sample holder that's optional on your TPS, whether it's on the MP1 or MP-V. So it comes in parts, and it's dividable, if that's the right way to describe it. It has an opening on the bottom, a cutaway for the TPS sensor, and then a top that you screw in place. And then once it's in place, you pour the rest of your powder in. So we'll assemble it and show the basic setup. So we're going to put it on the surface, add our powder. Just try to get a volume in there. It's not so critical that it be level per se, because we'll make sure that before we make a measurement, we do a small tap. We place the sensor in the opening and align the screws from above. And these just keep what are moving parts in one place. So we're not really applying any pressure through these. It just locks everything in location. The sensor's still aligned. And then we might tap it 3 times just to seat the powder. And then depending on your sample holder, whether it is a, this is the MP1 sensor adapter, there's an MP-V sensor adapter. We just slide that in until we see the contacts in the back. And then we have a sample setup with ambient density. Now normally we would take this weight and put it on. That would be the last step if you wanted to affix the weight, the density rather. And the other thing, the flexibility you have with using a weight like this is you can, if you put the top bar back on, you can apply, and if you graduate this portion, you can vary the density. So if you look at the change in height of that, again, this powder not being, it's quite stable in terms of density. Even if you do that, you get the same result. But if you had a material that was density sensitive, if you turn the set screw on top and look at the change in what's on the top, you can graduate that and see the change in density. So it's a little bit more flexible in that way, but you can do the exact same thing on the MTPS sensor. So we're going to move that over to the MTPS sensor since we can't seem to find the one for this one. Okay, so that's our sample setup for the MTPS sensor. We're going to go to the software and walk through the steps of making a measurement and go from there. Okay. So here's our main MP-V software. So again, the software for the MP1 MP-V are separated into 2 applications. One is data acquisition, which lets us schedule measurements. It's a smart, convenient application that gives us a lot of capability spread over a nice landscape of software. The second application is transient analysis, which is where we do calculations. What's nice about that is you can put that on your work computer, laptop, and you don't necessarily have to be in front of the instrument to do analysis. So we're going to name the user. If you want, point to where you want the results stored. In this case, we're just going to put it to the desktop. We're going to pick the modified or MTPS 3D source, isotropic, and semi-infinite. What are these other options? With that same MTPS sensor, you can measure single-sided anisotropy and single-sided slab. So this is a very capable modified transient plane source sensor that makes measurements in absolute way. What does absolute mean? Absolute means that from the raw data of the output of the sensor and system, the thermal properties are calculated. Thermal physical properties are calculated. And that provides a tremendous amount of flexibility. That flexibility being the ability to vary time and power. And I'll talk a little bit more about that. And that's the difference between the absolute version and the other version of MTPS that follows the standard for thermal effusivity, 7984. Something like that. So we'll go to the next screen. This recognizes the controller that's connected to it. If we had other sensors connected to it or temperature devices, they would show up here. We click next. Here's where we can name our sample. This is the dimensions of the opening. So the height that I filled the powder is approximately 10 millimeters. Again, that could be as high as the height of the opening, which is 25 millimeters. The radius of that opening is 12.5 millimeters. This is the high temperature MTPS sensor that's connected to the device. If you had a different sensor, it would be recognized there. We've already checked the sensor, and what that does, it electrically verifies the sensor is connected. The iTPS, so we've advanced the transient plane source method, both the symmetric and asymmetric, or ISO-2 and ISO-7, both. We've advanced the ability to really take advantage of an absolute technique that is very versatile with variable time and power, and really reduce the reliance on iterative development of parameters. And what I mean by that is we introduced the concept of the iTPS, which is the Intelligent Transient Plane Source, which is a proprietary measurement approach where the instrument measures and looks for the dimension of your material. So it knows the numerical representation, but when it's making its iTPS measurement, it's actually looking for the effects of reflection. So if you have a semi-infinite body and you measure past that semi-infinite body, the instrument knows that the time of measurement needs to be less than the reflection effect. So when it hits the boundaries, it bounces back. It can see that in the raw data, and it recommends a power and time less than the time it takes to cause reflections. So it's a very smart algorithm for determining the parameters. So it really reduces the necessity to iterate and develop your own parameters. Although it's a critical design element that we keep the ability to vary the parameters manually if you want to take a deeper dive or deeper understanding of your material. So both are possible. So in the measurements that we've run the iTPS, it's about a minute and a half measurement. We won't run it today. There's lots of demonstrations that show the iTPS run. The recommended parameters are 10 seconds and 25 milliwatts. Why 10 seconds is this material has a diffusivity. The instrument is continually calculating the diffusivity through that iTPS measurement, and it's recommending 10 seconds to stay within the dimensions of what is a sample size or volume of 10 millimeters high and 12.5 millimeters in radius. So we've already run that. So we'll run a quick transient, and then we'll schedule a measurement where we say run 5 measurements, and you can see that function. So we'll run a quick transient. Quick transient is designed as, I'm in this window, I want to ensure that the iTPS parameters are accurate, give us stable results and have good fitting, and then we can go on and set the schedule in place. And then we'll go to the transient analysis and share data that we measured on both the symmetric version, or the two-sided, and the asymmetric, or the MTPS sensor, and compare both. And you can look at the output of the instrument when measuring powders, or any other solid for that matter. So we'll let this run. This will run first it's balancing a bridge that's described in the ISO, and then it will run our 10-second measurement at the prescribed power, and then we can look at that early data and just schedule a measurement. So there's the time used is a bridge balancing, so that's a circuitry inside the controller that electrically balances a Wheatstone bridge, electrically balances the resistance, so that ultimately the change in resistance, the most sensitive region is at the double spiral at the sensor. So we're running our test. So the balancing is done, and we'll see a 10-second measurement result. Things always seem to take a little longer when you're looking at them. Maybe while that's running, I'll show you we can come back to that. I'll show you the transient analysis. So this is the data that was previously measured. So 10 seconds, 25 milliwatts. This is the MTPS sensor on titanium powder. There's our bulk or average thermal conductivity with repeatability, our thermal diffusivity with repeatability, and our thermal effusivity and volumetric specific heat. That's megajoules per meter cubed Kelvin. That same exact sample set up where the sample is on top and bottom, or symmetric configuration, is almost identical. So we can review data based off of a sensor measurement each, or you can review both of them just by selecting the different sensors. And that's what's really nice about the transient analysis software, is it allows you to bring together different different calculations by different sensors into one place and see how the results compare. So we have a 0.28 average of 5 measurements, and then symmetrically 0.279, so almost identical across the board on all the materials. And if you want to see those, I'll just leave this up for a moment. You can freeze the screen and compare. So volumetric of 1.55 and 1.63. And why it's so stable, if you were to sample this, take it apart, put it back together many times, is again this high fluidity and sphere-shaped powder tends to be very stable that way. So let's go back to our analysis, or our data acquisition. The measurement is done, finished tests. You can see what we want from this is we want a nice stable residual, and these are our quality indicators. There's no red highlighting there. So ideally, you want to see nothing, as in no colors. If something is not achieving the minimum temperature rise, these would be highlighted and recommendations would be made to change parameters. So the function of the iTPS is really to remove the ability to iterate to get to these quality indicators. Again, you can still do that manually, but the iTPS removes that. So the goal has always been with the iTPS, so that all you have to do as a user is input the name of your sample and the dimensions, the iTPS, and then the measurement of that does everything else. So we can schedule a measurement. So here we'll run 5 measurements with a 10-minute delay for 5 seconds at 25 milliwatts. This is an introduction of an initial delay so that when we make measurements and the output of the schedule, we have nice stable data with no temperature drift within the sample. So when we're scheduling measurements, it does 2 measurements in one. One is it records the temperature at the interface between the sensor and sample for stability. That's all automatic. And it's looking to see if your data is stable, isothermal. And we want to make sure that between each measurement, the heat introduced, which is only a few degrees, doesn't influence the next measurement. So that's all automatic. So this is the screen. When we enter schedule mode, this is the screen that you'll see generation of early data within the data acquisition and a event log of the various steps. So right now it's counting down a 10-minute delay. And once this is done, you can open it up in transient analysis and it will look just like this. So from here, we can export data. So if we want, we can dump it to Excel and you can see what that looks like. So this is that exact same data, just populated in Excel, and everything is exported along with batch notes or any other details you've noted inside your experiment. I think that concludes this demonstration of testing powders with the MTPS sensor and the Symmetric version. Or two-sided, both again almost identical for both MP-V and MP1 for testing these such materials. If you have any questions, please reach out to us. We'd be happy to answer or give a demonstration on your powder with both sensor types. Okay. Thank you for your attention.